Past paper question with commentary coming up, taken from the AQA specification on transition metals. This is from A-level chemistry year 2. So we've got a reaction scheme, pretty standard for these type of questions. The focus is on complexes of iron and their reactions. You need to work out, as you can imagine, in the following questions, the formulas for the precipitates, balance equations, the colours, the observations, so on and so forth. Take a good look at this question. You can pause it or take a photograph at this stage if you want to have a go. So our first focus is on reaction 1, and we can see that we've got an iron-free hexa-aqua complex, so the octahedral structure, iron in the coordination number of 6 or the coordination number of 6 of that complex, and we've added sodium carbonate to get a precipitate J. We need to give an equation as well as stating the colour and the formula. So the equation will get us 2 marks actually, because that will give us a precipitate J, and we need to know our colours, and there's really no getting around this, you just need to know the colours. So that's our precipitate J. Sometimes square brackets are used to represent a complex. I always used to use them to represent a complex iron, but I've seen in the mark scheme for this that we put square brackets around all complexes for AQA. So there's the FeOH free H2O free precipitate. It's neutral, so it doesn't dissolve in the water. So yeah, that's our precipitate. That's our solid. It's brown. Again, there's no way of getting to this unless you either know it or you don't. And there's the balance equation. Now, interesting to note here, how can we get to learn this a little bit more quickly? We've got an iron there, and we're reacting it with carbonate, and it's given us some CO2 and H2O. I think of the FeOH3 as a kind of a salt, and there we've got like a carbonate giving salt plus water plus H2O, which is slightly reminiscent of acid plus carbonate gives salt plus water plus H2O. And indeed, because of the highly polarizing effect of the Fe3 plus central cation, it weakens the OH bonds in the water ligands, so that it can donate H pluses. What do you need to remember? M3 plus, and for the AQA spec that involves Fe3 plus and Al3 plus. These tend to be more acidic, or they are more acidic than M2 plus. They are more likely to donate protons in aqueous solution, and hence there we go with the CO2 being involved there. Okay, so now we turn our attention to reaction 2. We are adding concentrated HCl, and we've got a solution containing complex iron L. Chloride ions can also act as ligands. So complex iron L is going to be a complex of Fe3 plus, but containing the Cl minus ligand. Chloride ions are much bigger than water molecules, and as such only 4 of them can fit around that central metal cation, so the coordination number is not 6 in the resulting solution containing complex iron L. It has a coordination number of 4, and it makes a tetrahedral complex, and there it is, the FeCl4 minus. The reaction is simply a case of, if you know what the reactant is and you know what the product is, we just need to balance for the ligands, and so we add 4 of those chloride ligands on the left hand side, and they are replaced or substituted, and the H2O ligands are also there on the right hand side, showing that they've been substituted. Okay, so next up we've got reaction 3. What's going on? Well, we are reducing the iron 3 to iron 2, so it's a reduction. You just need to come up with a good reducing agent, and in terms of the transition metal chemistry, you know that acidified zinc, from your knowledge of vanadium, and validates ions and complexes. the acidified zinc is a good reducing agent. So zinc, excess zinc in H2SO4 because it's a reduction. Okay, so yeah, again, just a knowledge-based question. This really, give the formula of precipitate M and state its colour. Sometimes NH3 can act as a ligand, but in this case, the NH3 aqueous, actually in water, NH3 exists as NH4 plus OH minus, so it can provide OH minus ions, and the precipitate is going to be the well, I'll give you the formula. There we go. It's the FeOH2 H2O4 precipitate. So the ammonia has provided us with those OH minus ligands there, and that's given us our precipitate. Simply a case of knowing the colours. It is green. You weren't asked for an equation, but just in case you are next time, I've put the balanced equation in there. It's balanced for charge on both sides, so that's something to keep an eye on as well. So finally we move away from that reaction scheme, and now we've got a different sort of task. We have to talk about isomerism in transition metal complexes. So the shapes and the types of isomerism, well, the type of isomerism that transition metal complexes can show is invariably stereoisomerism. We've got octahedral complexes that can display either optical and cis trans. We have square planar, which can just show cis trans. We also have tetrahedral complexes, which aren't really relevant to this particular example or this particular question. And there's also linear complexes, and again, they don't really show any type of stereoisomerism. Worthwhile knowing your definitions for stereoisomerism, particularly for organic chemistry, and also structural isomerism and isomerism in general. So you really need to know the diagrams inside out. There's a few that you can just kind of memorize and just always go to, and 3D diagrams will also be helpful in your year one studies as well. I've chosen to begin with platinum. Platinum can form square planar complexes. Square planar complexes can display cis-trans isomerism, and I've chosen the two examples of cisplatin and transplatin. Cisplatin, you should also know, is used as an anti-cancer drug. That's the trans isomer on the left there. You can see that the chloride ions are kind of north and south from each other or directly opposite each other, whereas here the cisplatin version, the chlorine ligands are on the left hand side as opposed to the ammonia ligands on the right hand side. Okay, so next we're going to take a look at the octahedral complexes. So cobalt can form octahedral complexes. Remember, we had to use the example of cobalt 2. These can display cis-trans as well as optical, as we discussed earlier. Optical isomers are non-superimposable mirror images, so it's definitely required that you put that definition in there and know it off by heart. Not superimposable mirror images, not mirror images. Optical isomers are non-superimposable mirror images. An octahedral complex with a coordination number of 6, they all have a coordination number of 6, requires 2 or more bidentate ligands to show optical isomerism. So a ligand is a species which can donate a pair of electrons to form a coordinate bond or a dated covalent bond. A bidentate ligand is a species that can form 2 pairs of electrons to form 2 coordinate bonds. Examples of bidentate ligands include the one in this case I've chosen is ethane 1,2-diamine, and there's the structural formula. Also the ethane dioate ion, it's worthwhile knowing that is a bidentate ligand as well. Okay, so now we need to draw the structures. I've chosen to do the optical isomers first of all, and so we've got our tetrahedral structure. Just memorize the where the dashes and the wedges go and try to visualize it in 3 dimensions. We've got the mirror image of that, and they will be non-superimposable. The dotted line in the centre there represents kind of the fact that this is a mirror image. Okay, so finally the last type of isomerism shown by the octahedral complexes is cis trans. So we can use the previous example, and that's the cis isomer. That will also come in a trans configuration as well. So the cis isomer is shown on the left there, and the trans isomer with the chlorine at the north and south pole, or the chlorines at the north and the south pole, show the trans isomer. So these are the cis and trans isomers.